Next slide. This slide is about grouping stars based on the easily measured intrinsic property of their temperature. We've already looked at the crude temperature measurement methods, the color, Wien's law, and filter comparisons. These give only rough measurements because stars are not perfect thermal radiators, so they don't produce perfect thermal continuous spectrums. A more sensitive, that is accurate, probe of a star's temperature is the presence of certain absorption lines and measuring their strength, that is how dark and fat they are. The picture shows a sequence of star spectra from a hot star at the top strip to a cool star at the bottom strip. Notice how the hydrogen lines in the hot star become weaker with the cooler star strips. The lecture slide and textbook go into a bit more detail about what's happening at the atomic level to make the absorption line strength of hydrogen change with temperature. Similar things happen for the other elements. When you cross-reference the spectral line strengths for all the different elements, ions, and molecules, you can derive the temperature of a star to within 99% or better accuracy. The spectral types in order of their temperature from hot to cool is O, B, A, F, G, K, M. As the lecture outline says, memorize the order. The memory aid I use for the order is Oh, be a fine girl or guy, kiss me. You choose the gender. If you memorize the order, then you will automatically know a lot about the stars because that is also the order for the masses, from high mass to low mass, from large size or diameter to small size, from very luminous, of many thousands of times more than the sun, to dim, many thousands of times less than the sun, from very rare to very common. The M-types make up 75% of the stars in the galaxy, but G-types, like the Sun, make up just 2% of the stars, and O-types are just a fraction of 1%. This is also the order from very short life of just a few million years to a very long life of over 1 trillion years. Every single K and M-type regular adult star that has formed in the universe is still shining. Note that this order is for regular adult stars. We call them main sequence stars. 90% of the stars in the universe are regular adult main sequence stars. The other 10% are oddballs that do not have this order of temperature, mass, size, luminosity, and so on. Next slide. This slide is about the Hertzsprung-Russell Diagram. To see how stars are constructed, check for relationships between intrinsic properties. Two different astronomers in different countries, independent of each other, found a relationship when they plotted the temperature versus the luminosity. This plot is called the Hertzsprung-Russell Diagram in their honor. The dots are not randomly sprinkled around the plot. There is a relationship. That tells us that nature prefers to make particular kinds of stars. Understanding why enables us to determine the rules that nature follows. If a star is large in diameter, it will also tend to be hot and have a large mass. If the star is small in diameter, it will also tend to be cool and have only a small mass. There is only a small percentage of stars that don't follow these trends. There are some large but cool stars and some small but hot stars. 90% of the stars in the universe are regular adult stars on the main sequence. The other 10% are oddballs in the last stages of their lives and are the subject of another lecture. The giants and supergiants are cool but luminous stars in their dying stage of their life, and white dwarfs are the dead cores of stars slowly cooling off. Our Sun is in the middle of the main sequence strip. So the question is then, is the Sun a typical or average star? Next slide. Is our Sun a typical star? That's the question for the next few slides. Compared to apparently bright stars, ones that are visible even from the center of a city, the Sun is relatively cool and dim. How you select your sample, that is, group your stars, can strongly affect your results. Next slide. Compared to the nearby stars, that is, ones within just a few parsecs of us, the Sun is hot and luminous. How you select your sample can strongly affect your results. Next slide. What is a typical star depends on how you group your stars, how you sample the population. Here are proportions of the different spectral types in the two samples. Most of the stars within a distance-limited sample are small, cool red or orange stars, the K&M types, while most of the apparently bright stars are extraordinarily luminous hot blue or white stars, the B and A types. How you select your sample can strongly affect your results. I've been talking about star populations, but the statement is true of any group of things or people, especially people. A good political poll uses a sample that properly represents the general population. Next slide. A representative sample is a collection of objects that includes all parts of the population of the objects in their proper proportions. It is an unbiased sample that gives accurate results. In a typical patch of the galaxy, the most common star type is the M type, the small red dwarf stars. About 75% of the regular adult stars are M type. They are like grains of sand on a beach, while the A and B stars are like the few big rocks found here and there. The K and M types are all the red dots, while the A and B stars are the blue dots. The sample that is very biased is the apparently bright star sample because it only picks out the exceptionally spectacular luminous stars. It picks out the one that you would see under even the worst of conditions. The near star sample is representative of the galaxy's stars. There are more K&M stars in a distance-limited sample because there are really more K&M stars in the galaxy. In fact, a distance-limited sample of any type of glowing astronomical object is a more unbiased representative sample than a brightness-limited sample.